let's see. We have this one. No, this one. Okay, it should be streaming. So, any question from this time? So, as we said, we will skip the rest part of chapter 2 and we'll start in chapter 3 today. Chapter 3. Okay. Control L. Yeah, and I guess a quick review about chapter 2. So last time we were talking about the unit doublet and triplet, those very singular singularity functions who are the derivatives of delta function. And when you convolute those u2, u3, etc. with your sum function, you get the case derivative. Yeah, so you convolute uk with x of t, then you get dkx dt, the case derivative of x. But let's stop thinking those for now, because we are going into a pretty different topic today, chapter 3. It's a Fourier series representation of periodic signal. Okay, and okay, so that's a lot of things, and let's start with a quick historical preview. So the idea of this chapter is we want to represent the periodic signal with the linear combination of harmonic series. So those are harmonic series, although they are real, so a little different from our definition. Remember, the harmonic series are e to the jk omega t. But if you take the real part and look at this, so for some period t here, then we have those harmonic series. And so if you take a linear combination of them, they are still periodic in t. And so you can represent a lot of periodic signal with linear combination of those things. And so here is a picture of Fourier. Yeah, so Fourier started, well, not quite start, but I guess did a lot of work in this Fourier series representation, where you write out a lot of periodic signal in terms of the linear combination of those sinusoidal functions or complex exponentials. But so here is a little history story. So Fourier's work doesn't actually get accepted by his time, because his work was strongly rejected by Lagrange. Because Lagrange think you're doing this kind of thing doesn't make a lot of sense. So for example, what if your periodic function look like has a sharp corner here like this? Okay? So if your function look like a sharp corner and keep repeating yourself, and we will see in this course that we will represent this kind of thing in terms of Fourier series. But you see all those sinusoidal, they are very continuous and smooth, right? So this is differentiable everywhere, but if your signal has a sharp angle here, then it's not differentiable here. So how do you add up a whole bunch of signals that are all differentiable and get something that's not differentiable here? That doesn't make sense to Lagrange, but we will see how do we deal with that or ignore that later part in this chapter. Okay, so that's a quick historical review. And once again, here is a picture of Fourier. And anyway, so let's jump into the actual mathematical representation of the chapter. Okay, so first we want to get a quick review about our complex exponential. And okay, so this is e to the st, so those are complex exponential we talked about in chapter 1, and we're going to see what are useful here very soon. And also the counterpart in discrete time, those e to the n. And what are useful because they're actually eigenfunctions for all LTI systems. Okay? So it's very interesting. So remember LTI system is, well, it's a system that's linear and time invariant. And the system is something you get x of t to y of t. And what do we mean by eigenfunction means that you put those eigenfunctions x of t inside your system, then you get some y of t that's proportional to your x of t. So your y of t will be lambda times some x of t. Okay. And yeah, so it's like linear algebra. Not sure, you probably all learn a little about matrix, right? So you can think this like infinite dimensional generalization of your matrix equation, the eigenvalue equation in terms of matrix, right? So the eigenvector for your matrix will write like A times V equal to lambda times V. So it's a similar idea. So for matrix and the vector, you have your matrix, linear matrix, times your vector becomes proportional to your vector. And here we think about those LTI system. You apply your LTI system to your input x, and you get the output that's proportional to your input. And that's called the eigenfunction. And so a very cool property about LTI system is that actually all of them have the same eigenfunctions. So it's all those e to the st or z to the n for continuous time and discrete time. Okay, so every LTI system has the same eigenfunctions. So the only difference of them are the eigenvalues. Okay, and also another spoiler. So comparing to chapter 2, we are doing something similar but different. So chapter 2. We are analyzing LTI system, but considering we decompose the input into those impulse functions, right? We are saying x is a summation of a whole bunch of impulse function, and we see what's the response of your system to each impulse function. And here we are going to write our input x as a summation of a whole bunch of eigenfunctions. And the eigenfunctions are those two things. And then we will see the response to the eigenfunctions for the eigenvalue times the eigenfunction. Okay, so that's a lot of spoiler, but let's first see the thing we yeah. So let's first see the thing we excuse me, we convince is true. So we said it's e to the st and z to the n eigenfunctions for continuous time and discrete time LTI system, and that means that you put the e to the st inside the LTI system, you will get some eigenvalue h. Eigenvalue we call it h, and the h will be a function to this s, because for different s that's a different function, right? So we get some h of s and times e to the st. And similarly for discrete time, this eigenvalue will be a function of this z. Okay. So yeah, we will prove these two equations very soon. So you put e to the st into any LTI system, you will get h of s times e to the st as the output. And this h of s will depend on your system. And you will see the big h of s. Well, it's h, so it looks very similar to your small h of t, right? So they're actually related, but for now we will not talk about the relation anymore too much. But in chapter 4 and 5, we'll see the big h are very closely related to small h. Okay, you can change it back and forth. But anyway, this big h is a very important characteristic. This big h actually tells everything about your LTI system, and we'll call them system function, or system response, or transfer function. So those are all things we will see in various textbooks. Maybe more if you are a double E major. Okay, so remember those names. Okay. And but for now, we think those h are the eigenvalues of your e to the. So this h of s is the eigenvalue of e to the st. Okay. And as we said, the eigen equation is like for matrix a times v equal to lambda v. Okay. Okay. And okay, I guess before we do go into proof, any question about the meaning of those? If not, then yeah, let's go into the proof. The proof is pretty straightforward. So yeah, we just say, well, we see this is eigenfunction, so let's see what happens if we put the eigenfunction into our system. So we have input e to the x, input x of t equal to e to the st. And well, we have our LTI system, and LTI system is described by some h of t, right? And we spend this whole chapter saying that if you have a LTI system, then output is a convolution of your input with your h. So here is the convolution with of your input with h. And here we use a little property of the convolution. We use that the convolution is commutative. So this is h convoluted with x instead of the usual x convoluted with h. But anyway, this is correct. So this is h convoluted with x. And yeah, and we know our x is e to the st. So let's put in, just plug in the x. So now this t is actually t minus tau. So we have e to the st minus tau. Okay, and then we break up this exponential into e to the s times e to the st times e to the minus s tau. Okay. And but this integration is integrating over tau. So e to the st is actually just a constant for this integration. So we can move with this outside of the integration. Okay. And we get this relationship, this equation. So for any LTI system, y of t equal to e to the st, and integrating over tau, h tau times e to the minus s tau. Okay. Quadrant here. And if there is no quadrant, we are almost done. Okay, so this e to the st is our input. So we already got our input back, and we got a whole bunch of complicated terms here. Those whole integration about tau. But the important thing to see here is that this whole integration has no dependence on t. Okay, yeah, this whole thing they don't have t anywhere. So in terms of t, this is just a constant. So there are a lot of dependence on tau, but tau is just something you integrate over. So it don't really depend on tau either. It's just a function of s. Okay, because tau is basically a dummy variable that you integration over. So the whole thing, there is no t, and the tau will integrate over. So this is just some function of s. So we just call it big H of s. Okay, and yeah, so we have finished our derivation. So I guess the only thing we do is we write down the convolution and we break up this e to the s of s times t minus tau, and then basically follows y equal to h of s times e to the st. So this is as promised for every LTI system. For every LTI system, this e and any s, e to the st is the eigenfunction of your system with the eigenvalue h of s. And here we have seen how to express h of s in terms of small h of t. So big H of s is the integration of tau, h of tau e to the minus s tau d tau. We are going to see more about this here. So you can see that you can calculate h of big H of s for AVS from the small h of t by doing this integration. And in chapter 4, you are going to see the inverse. But for now, we just know that this thing exists for AVS. Okay. Well, not quite bad. The existence is also weird, but for now, I just think h of x exists. Okay. 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 Any question? Yeah. So I guess a little spoiler. So later, as a very late part of course, you will see that this actually has some trouble because for some s, this integration doesn't converge. So yeah. So then that will give you some trouble. But for now, let's assume this converge. And actually, if s is purely imaginary, it will converge, and that will be nice. Okay. But for now, let's just know that e to the st will be for some complex number s will be eigenfunction of your LTI system. Okay, question about the derivation. Okay, if not, then yeah, we see that h of s is the eigenvalue and is associated with the eigenfunction e to the st. And then we do another derivation, and we say, so that's for continuous time. And for discrete time, we say the eigenfunctions are those z to the n. So z to the n is basically e to the st, but sampled on integer values. But and anyway, we will do the very similar derivation. So x of n equal to z to the n, and we just plug in the convolution. So discrete time convolution h convoluted with x equal to the summation of k from minus infinity to plus infinity h of k x of, oh, I should say k here. Okay, so let's mark this down. This is k from minus infinity to plus infinity. Okay, and h of k x of minus k. And yeah, and we say we plug in the x. So this x of a minus k is just z to the minus k. And just like before, this summation only depend on is only summing over k. So this z to the n is the constant. So plug z to the n out, and you see this whole thing is just summing over k. And so this is the function of z. Okay. So I try k here. Okay. K. And yeah, so by the very similar argument, we see that this expression is just z to the n times some big H of z. Okay, so we call this big H of z. And here we get the expression of big H of z. That's sum from k from minus infinity to plus infinity, h of k z of minus z to the minus k. Okay. Question about derivation. Okay. So yeah, so those will be very important in the later chapter. But for now, this is just a derivation here. And yeah, so for the purpose of this chapter, we just want to show that e to the st and e to the n are very important for LTI systems because they are eigenfunctions. And okay, so those are just words, and here is the summation. So once again, e to the st for complex number s is eigenfunction. They are all eigenfunctions for LTI system. They will go to some h of s e to s of t. So output will be h of s, big H of s e to st, where big H of s can be expressed from small h of t like this. Is the integration h of t e to the minus st, sorry, h of tau e to the minus s tau d tau. I guess you can also write t here because it is a dummy variable. But anyway, and for discrete time, z to the n for any complex number z is eigenfunction for your LTI system with eigenvalue big H of z. And big H of z can be calculated from small h of n, summation k from minus infinity plus infinity h of k z to the minus k. Okay. And e to the st, z to the n are eigenfunctions, and big H of s, big H of z are eigenvalues. And a lot of things can be complex number. So those s can be complex number, z can be complex number, and big H, big Z can all be complex number. Okay. And okay, there is no question. Then, as we said, those e to the st are eigenvalues. Are eigenfunctions. So we want to write our for the x that are not, for x that are not just e to the st, then we want to write them as a linear combination of those eigenfunctions, right? So for general x, we want to write general x in terms of e to the st. So we write the summation k with some coefficient ak and e to the skt. Yeah, for some xk. So if we can write our input in this form, then the output will be very simple. It's even simpler than what we're doing with impulse function because those are eigenfunctions. And so you put eigenfunction into your system, we'll just get back your eigenfunction and times your eigenvalue, as we just say. And the system is linear, so all those linear coefficients you just add together. Okay. So yeah, if we can write our input in this form, then the output we can basically directly read in a very similar way, in a very simple way. So just the output is basically the same thing, but the AK will get multiplied by some H over SK. Okay. That's very cool. And for this kind, it's very similar. If you can write your x over n in terms of summation of some zk to the n, some zk to the n, and then the output will just need to multiply with those eigenvalues in front of your zk to the n. Okay, question? No? Then if there's no question, then let's see a very easy example of how the thing are correct. Okay? So we have a very easy system here. It's a time delay system. So output y of t equal to x of t minus 3. Okay? And from what we say from on the last chapter, the impulse response will be, actually you can just calculate directly. So you put the x of t equal to delta of t, then obviously y of t will be delta of t minus 3. Okay. Although we write tau here, so I should probably say t here. Okay. So we want to say h of t equal to delta of t minus 3. Okay. This is impulse response small h. Okay. And okay. Then we see that if we put x of t, now we try some eigenfunction. So we have s equal to j2 here, j times 2 here. Remember, j is the imaginary number symbol in the course. Okay? So let's see, this is actually an eigenfunction for this LTI system. So let's do a direct calculation. So y of t equal to h of e to the j2, and t become t minus 3. Then j2 t minus 3, then you see that you get back your e to the j2 t here. Then you have a HR term is j2 times minus 3, so you take the HR e to the minus j6 here. Okay? And you see that this is indeed proportional to your input. This is e to the minus j6 times your x of t. Okay? So indeed, the x of t, this is the eigenfunction. Okay? And we can also do this calculation in other way. So we can calculate our big H of s. Okay? So big H of s from the formula we had before is you integrate your small h of t and times e to the minus s tau and then d tau. Well, h of t or h of tau equal to this thing. Then this will give you do the shifting property of delta function. This will turn your tau here equal to 3, okay? Because this is only non-zero when tau equals 3. So this turn tau equal to 3, then you get e to the minus 3s, okay? And this is true for every s. Okay. And well, yeah, it is converged for every s. yeah, and then you can calculate your eigenvalue from directly reading this h of s. Now you put s equal to j2 because you see this here we have a purely imaginary s equal to j2. This is e to the st, so s is purely imaginary j2, and h of j2 then plug in, then that's sen e to the minus j6. Then as the eigenvalue you calculate here by plugging your x directly into this relation. Okay, so we see that everything we say makes sense. E to the st is indeed the eigenfunction for this LTI system, and the eigenvalue is what we expected. Eigenvalue is this integration. So this big H of s is this integration of small h times e to the minus s tau. Okay. Question about the example? Not. If not, then let's see this is a little more. Okay. And as we said, we have our system with h of tau equal to delta of tau minus 3 and h of s equal to e to the minus 3s. And now we give it a more complicated input. So if our input x of t is this, is this working? If our input x of t is this, excuse me. Hello? Hello? Okay. Anyway, x of t is this cosine 4t plus cosine 7t. Then obviously from this relationship you can calculate your y of t very quick. It's just cosine 4t minus 3 cosine 7t minus 3. But we can also break this into the eigenfunctions. And here this is easy to break it into the eigenfunctions because it's just cosines. Okay? And so let's just do this. So we do this reverse Euler that we like a lot. So we break cosine equal to 1 over 2, cosine x equal to 1 over 2 e to the jx plus e to the minus jx. So this is how you break cosine into linear combination of complex exponentials. And so this cosine 4t becomes 1 over 2 e to the j4t, 1 over 2 plus 1 over 2 e to the minus j4t. And similarly, you break this cosine 7t to e to the j7t to the minus j7t. And then you try to do the output by using your eigenvalue equation. So we want to do this thing, right? So now we already write x in terms of summation of complex exponential. Then we can write the output as a summation of complex exponentials with those eigenvalues. So eigenvalue will be e to the minus 3s. So here we have s equal to j4, so minus 3s will be minus j12. And similarly, we have this h of s equal to e to the j12, and then here we have minus 3 times j7 minus j21 and plus j21 here. Okay, so we can have y of t in this form. So we already have y of t here, and but I want to compare it with this. So let's try to clean this up into cosine and the cosine once again. So we combine those exponentials, and you see this is exponential j4 times t minus 3 and etc. So all those with t minus 3, and then we do our then we see this is in the form of those reverse Euler, and so this is e to the jx, e to the minus jx. So this combine back to cosine, and this combine back to cosine. Okay. So anyway, once again, we see our formula makes sense. If our x over t equal to this cosine 4t plus cosine 7t, then we can express this in terms of linear combination of complex exponential, then we can calculate the output as the complex exponential times their eigenvalues respectively. Okay. Okay, question about the calculation here. And yeah, so we see that everything works here. And obviously for this system, it's easier to just plug in the definition here to get the output. But for more complicated system or system expressed in different form, we'll see that this eigenvalue expression so expressing the system in terms of this big S is very useful. Okay. And this kind of representation, we call it a frequency domain representation of LTI system. Okay. Any question? And we have 20 minutes. Okay. If not, then we'll actually stop thinking about system for a while. Okay. So now we're back to analyzing signals. So the previous section is kind of like motivation. So we are motivated, so we'll have a motivation to want to express our x of t in terms of whole bunch of complex exponential, because we see if we have x of t in this form, then you can calculate y of t pretty easily if you know this big H of s. Okay. Yeah. So we want to write x of t in terms of complex exponentials, and then we'll start. So we'll start to talk about how to write a signal in terms of summation of complex exponentials. Okay, and so those kind of things is basically what the Fourier transform do. Okay, and but for now, and there's a lot of Fourier transform for different functions. For now, we start with probably easiest case, which is the Fourier series representation for continuous time and periodic signal. Okay. So here the important quantifiers are continuous time and periodic. Okay. And so yeah, we want to do this on periodic signals. So let's first get a review on periodic signal, because it's been quite some time. We talk about those in chapter 1. Okay. So chapter 1, we say a signal is periodic if there is a period big T such that x of t equal to x of t plus big T for time t. Okay. So you can shift your whole signal with this big T, and the signal will stay the same. Yeah, and so big T will be a period of your signal, and then there is a fundamental period, which is the minimal big T you can find, minimal and positive. Okay? And also we define, and so that's a fundamental period. Then from fundamental period you can define a fundamental frequency, which is just 2 pi over your big T. Okay? Remember that there is a definition chain. So you have a periodic signal, then you can find the fundamental period as the minimal period. Then you define fundamental frequency as 2 pi over your fundamental period. Okay. So that's a quick review of periodic signal. And then in chapter 1, we see 2 signals that are very periodic. Okay. So we want to talk about real functions. Then we have those sinusoidal signals. So x of t equal to cosine omega naught t or sine omega naught t. They are different forms. Okay. And or you have the complex exponential. Now these look like very similar to what we want, right? So with our e to the st with its purely imaginary, then we have those complex exponentials, x of t equal to e to the j omega naught t. And remember, those e to the j omega naught t are always periodic. And anyway, e to the j omega naught t, they have fundamental frequency. Okay, I'm missing a knot here. Okay. So they have fundamental frequency omega naught and the fundamental period 2 pi divided by omega naught. Okay. So the omega naught here is the fundamental frequency. And then we have a very interesting concept of harmonics related complex exponentials. So there are a whole bunch of e to the j omega naught with the omega naught relating to each other. So we are abusing a notation a little bit here, but then we say psi k. So anyway, so a whole bunch of harmonically related complex exponentials, they are sharing the same omega naught, and they are labeled by those k, and the value of those harmony related exponential, so excuse me, not quite value. So those functions are e to the jk omega naught t. So they have their frequency being omega naught times some k, okay? And the k will be any integer. So 0, plus minus 1, plus minus 2, etc., all the way to plus minus infinity. And if you want to write this in terms of big T, this will be jk 2 pi divided by t. 2 pi divided by big T and times small t. Okay. And okay, so those things. And as we saw in chapter 1, those functions, well, each of them have the fundamental frequency k omega naught, and you will see then you go this other way around, then the fundamental period will be t divided by k. And well, except for k equals 0, it's a weird one. It's like periodic is undefined with being a constant function. But for non-zero k, those functions has period t over k. And we also see in chapter 1 that if your function is periodic with some period t, then t times some integer is also your period. And so the big T is actually a period for all those harmonic functions. Okay? Harmonic complex exponential. Okay? That's the interesting thing about them. So they are all periodic with period T. And actually we are going to see the reverse today. We're going to see that everything periodic with period t can be written as a linear combination of them. So just like this. But I guess that's a spoiler. So, but for now, we just take a linear combination of those harmonic exponential. So we have e to the jk omega naught here. And so we sum over different k. So k from all the possibility from minus infinity to plus infinity. Then we have some linear coefficient ak here. Okay? So we can think about function in this form, x over t equal to some k from minus infinity to plus infinity, ak times those harmonic complex exponential. This e to the jk omega naught t. And you can also write omega naught instead of big T. And anyway, we say all of those are periodic with period t. Then a linear combination of them should also be periodic with period t, right? Okay. And yeah, so we can write a lot of periodic function in this form. Okay. So this is the main focus of today. We'll talk about how to express signals in this form and properties of expressing signal in this form. And yeah, so a few let everyone look at this once again. So x of t equal to summation k from minus infinity to plus infinity, ak e to the jk omega naught t. And So if you write a periodic signal in this form, it's called the Fourier series representation. And a few more notations to call. And so first thing to notice that if k equals 0, then you have e to a 0, then this is just a constant term. And if your k equal to plus or minus 1, then those terms have fundamental frequency equal to omega naught. So they are called fundamental component or first harmonic component. And more generally, if your k is plus or minus n, then that component called nth harmonic component. I think that's pretty intuitive, right? Okay. Any question about this linear combination of harmonically related complex exponential? For now, we are just summing together a whole bunch of complex exponentials. Okay. So this is some function. And here's another way to see this. Just a reminder. So x of t will be summing over all those harmonics from minus infinity to plus infinity. Okay. Okay. First harmonic, second harmonic, etc. Okay. So I guess let's see example. There is really not much here. Okay. So we have x of t. So we have a finite range of k in this exponential in this example. So here we have k from minus 3 to plus 3. And so ak, we just release them here. So a0 equal to 1, and a plus minus 1 equal to 1 over 4, then plus minus 2, a plus minus 2 equal to 1 over 2, a plus minus 3 equal to 1 over 3. So there's nothing special here, we just put some number here. But I guess the special thing here is the plus minus k all have the same value, so we can write x of t in a nicer form. So if we write a summation with the plus and minus these things together, so you see we can write all these for different k. So we have the a0 term here, a0 equal to 1 times this k equal to 0 is a constant. And then we have the plus minus 1 term here, so a1 here, and e to j plus 1 omega t and j minus 1 omega t. We'll see the omega naught equal to 2 pi here. And then we have k equal to 2, k equal to 3, k equal to plus minus 2, k equal to plus minus 3 here. And we see we have a nice symmetry here because those plus minus k here. Plus minus k term has the same amplitude. So they can be combined into cosine. Just once again use our reverse Euler. Okay, so this is 2 cosine 2 pi t, and this 2 cosine 4 pi t, and this is 2 cosine 6 pi t. Then you multiply your coefficients, you get this. Okay, so you see x over t is the sum of cosines with different frequency, and we can see them in picture here. So here is your a1 term, and here is your plus minus 1 cosine, plus minus 2 cosine, and plus minus 3 cosine. And you can add them one by one up. So you have a so you have your k0, and then you plus your plus minus 1. Sorry. So you have so we call these x1, x2, and x3. And you have x0 plus x1 equal to this thing, so it is still periodic with period 1, and then you add up this signal with this extra cosine, and you get, well, some weird oscillation. So some of those cosine you like hit together, so you have higher peak, and some of them cancel, you have lower peak, etc. But you see this is still periodic with period 1, and then you the x3 with a higher frequency, then you get a weirder signal, but it's still periodic with period 1. Okay, so this is just an example of x as a summation of complex exponential, and we have a nicer amplitude here. So I guess not quite amplitude, it's coefficients. So we have a nice coefficient here, so we can express x in terms of these real value functions. So then we plot a real value function. So you see how all those cosines adding together into increasing signals, but it's still periodic. Okay, and we have 5 minutes. I guess any question for now? Okay, let's keep going. 5 minutes. Okay, and as we said, this signal has a nice property that it gives you a real signal even though you have a complex exponential. So let's think about what periodic signal will give you is actually real when you summing over all those complex exponential. Okay, so once again, our x of t is this summation of complex exponential with coefficient nk, and let's assume x of t is real and see what condition we can get. Okay, excuse me. And yeah, x of t is real. If x of t is real, then x of t is equal to the complex conjugation of x of t, so x star of t. Then you take a complex conjugate of this thing, then ak obviously becomes ak star, because ak can be complex. And the larger part, excuse me, look at the complex exponential is this e to the jk omega naught t. Yeah. So you get a complex conjugation, is j becomes minus j basically. Okay, so is e to the j something become e to the minus j something. It's just and then, but we want to compare this to our original form where we don't have a minus sign here. So we do a change of variable. So we change k to minus k. Then you can k to minus k, you will cancel out the minus sign here, and then the ak become a minus k, and summation k is still minus infinity to infinity. Okay. And okay, so we see that x of t will equal to this summation. This is a very similar form, but instead of ak, you have a to a star sub minus k. And here we use the thing that we'll prove very soon later. So when you write the function x of t in this form, in this Fourier series representation, the ak is actually unique. So if x of t equal to this thing and also equal to this thing, then this a star minus k must equal to ak for every k. Okay? And so we arrive this conclusion that if our x of t is real, then ak must equal to a star of minus k for every k. And this is actually a quite important thing. We will see this thing in all different forms of Fourier transform. And yeah, so this is something worth to remember, and it's also a nice thing that you can do to sanity check your calculation. So if you have some real signal and you calculate their ak, then you can check it out. This thing is actually satisfied. So I guess we can check it with our example 3.2 very quick here. So I guess another way to see this is you can move this star around. So you have a minus k equal to ak star. Yeah, that's quite a nice form. A lot of times you will use this. It also means a k star equal to a to the minus k. Okay, and you see that's actually true here, right? So all those a are real. So a star equal to a and a equal to ak. So excuse me, ak star equal to ak, and we have ak equal to a minus k. So let's check out. Okay, so that's nice. And 1 minute. 1 minute. I guess we can stop a little early now. So let's resume in 4:30. We'll finish those real part discussion. Hello, hello. It's working. Volume. Oh, hello, 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 hello. Oh, this way.你先放这里吧，主角还没有来。
啊，刚才我有事情，我的肚子有事情去厕所。
哦好。这样。
所以第二章还没教的部分是？
就你可以看，但是不会考的。
哦，不会考。
对，基本上不会考。这样。
那个之前的作业有大概知道什么时候会发回来吗？
都还没有发吗？好像你可能是助教，
纸本的还没发回来。
他好像每个礼拜都会带来这里，然后你也可以去那个助教办公室外面看。就他在支店445、444那里。对，他应该是有放在外面的盒子。
哦，OK， 好。
比想象中快。
他说还有一张是那个应该是会发到你
发到我
那个教室
哦，那我去找一下。
好像主要是他那张要交回去给他。
哦 ，OK， 那我去找一下。对。他什么时候要？已经过期了，是不是？
应该就是尽快拿给他之类的。好。
那张是你要签吗？
那张应该。
也是那张是因为上次老师那边确认说要花多少钱，然后这边是学生这边。
我记得那一张是有你的学号跟那个。
应该是要。
我应该找到。
对，第一个应该就有。
OK。学号跟 email 应该一人应该都有。
我看一下，有需要我再丢给你。
好。我们进去楼上。那小地方应该可以交吧？不要交那么快啊！这2个礼拜考试嘛？
对。他那个同学有来找你，那个我之前有一封寄信问我说有补考那个要找你，
我都没看到信哎。
他没跟你讲。我叫他
应该是我叫他寄给我，然后CC寄嘛，所以如果是我看一下这是什么？我没有看到的印象。Hello, OK， 喂，这样子 ，Hello，好像对不太到，不管，about this，OK， does this work? A little. Anyway, okay, let's back to our real periodic signal. Okay. So we have our signal in terms of those harmonic complex exponentials. So x of t equals to summation k, aka to the jk omega naught t. And we see that if x is real, then ak equal to a star minus k, where this star means complex conjugate. And if ak equal to a star minus k, then we can clean up this summation into nicer form. We can make it into sine and cosine. So let's see the derivation. So x of t, now we want to pair the k with k. So we see there's a symmetry between k and minus k, so we want to pair the ak and a minus k together. So first we write this summation. So we separate out this a0 term. Then we have summation from 1 to infinity. And ak and a minus k. So nothing really happened here. We just change the counting here. So we have k, and we just write minus k here. So for every negative k, we write it as negative or plus k. And then we use this condition we derive here. So a minus k equal to a k star. As we said, this is something we use more often. And so a minus k equal to a k star. Okay. And yeah, so we have summation. And from this relationship, you can also put k equal to 0 here. Then that'll give you a0 equal to a0 star. So a0 should just be real. Okay. And you have other term equal to this thing. And then you see that these two terms are the complex conjugation of each other. Because, well, if you get a complex conjugation, the ak becomes ak star, and this e to the jk becomes e to the minus jk. And so this is a naught plus the 2 times the real part of your ak e to the jk omega naught t. Okay? Because it's a complex conjugation of each other, so the imaginary part will cancel out, and you are left with the real part, and that satisfies our. This is what we expected because, well, this is a real function, so you take only a real part. And anyway, so this is taking a real part, and now we express ak in the polar form, so ak equal to some amplitude big AK times e to the j theta k, so some phase here. Then you can write this as AK, and you can keep the phase together with this exponential, so e to the jk omega naught t, what you already have, and plus h cross theta k, you get it from your small ak. And finally, now you use Euler formula. So this exponential is cosine theta plus j sine theta. And j sine theta you can just throw away, so you left with cosine theta. So, because you are taking a real part. Then finally your x of t equal to a naught, which should be the real. And then you have 2 and summation k from 1 to infinity. AK cosine, now all those things, k omega naught t plus theta k. And ak and theta k are coefficients that depend on your signal. Okay. So here is a form of expressing your real periodic signal. Okay. Question. And you can also do this in another form. So you are basically breaking this cosine into. So if you don't want the theta k modifying your k omega naught t, then there are two ways to see this. One way to see this is you break this cosine into the sine and cosine, right? So cosine plus b equal to cosine minus sine. But we want to see the derivation in another way. So another way to see this is you break your ak in rectangular form instead of polar form. So your ak equal to bk plus, so big bk plus j big ck, and then bk and ck are real. And okay, so we need to switch this back and forth. So you think about, you put ak equal to bk plus j big ck here, and taking a real part. So the real part should be the real times real, which should be bk times cosine this thing. And another real part is you have j times j equal to -1. So the j ck times j sine theta, not theta, j sine something should be minus ck sine something. Okay, and yeah, so this is what you get. So real part will be this real times real and the imaginary times imaginary. So this is j ck times j sine k omega naught t, and the other bk cosine omega naught t. Okay. So instead of expressing this in ak and theta k, you can express them in bk and ck. So bk times cosine omega naught t minus ck sine k omega naught t. Okay. So there are two forms of expressing your real periodic signal. Okay. And yeah. And well, you can see that they are real because all the coefficients are real and the sine function, cosine function are real. So that's pretty nice. Okay. And I guess we can. Something to check is as some sanity check you can do is you can check the number of degree of freedom in your expression. So you see that here you have for every k you have ak and a theta k. So it's like two variables for every k. And here you have a bk and a ck. So check out. So for every k there are two variables here, and two real variable. And here for every k you have two real variable. So they corresponding to each other. Maybe because it's basically the rectangular form and the polar form of your small ak. Okay. And I guess another thing to check is why there's two variable for every k. So remember for x, so for x over t you have one variable for every k. But here for every k is both representing the negative k term and the positive k term. So here for every k we have a complex ak, and here for every k we have two real value coefficient. And so it's either ak theta k or bk ck. Because instead of summing k from negative infinity to positive infinity, we have a k are all positive here. Okay. So the variable counting kind of work out. And back to example 3.2. So example 3.2, we have just a summation of a whole bunch of cosine. So remember 3.2 is this thing. So here this is a extra simple case because all those ak are real, and so actually those two forms have the same expression, because if you do only polar form you will see a ck equals 0, and you go to this is a polar form, so you go to polar form you see the theta k equals 0, then you go to the rectangular form and you see the ck equals 0. So it's just summing over cosine k omega naught t. The same expression. Okay. And any question for the real representation? Representation of real periodic signals. You can do cosine with theta, or you can do sine cosine. And actually, you can also do sine with theta, but that's probably more annoying. Okay. And if there is no question, then let's go to the, I guess, most interesting part of the chapter, or most important part of the chapter. Okay, so we want to write our periodic signal in terms of our Fourier series representation. Okay, so we have a periodic signal with some period big T, and it satisfies xt equal to x of t equal to x of t plus big T. And we want to write in this Fourier series. So summation ak e to a jk omega naught t. And another problem is if we are just given some function, then how do we find the AK? So in a previous example, we have our function is something very simple. Then, okay, it's a very long time ago. So previous example, we have x equal to just cosine and sine. Then we can break up cosine and sine into complex exponential because we have our reverse order. But if our x is given in a more general form, how do we do this? And we can actually calculate this with a very closed form formula. So we can calculate those AK with a closed form formula by noticing this inside. So actually all those different JK omega t, those harmonic functions, they are orthogonal in the following sense. Okay, so they are like, so it's how do I say? It's very similar to our matrix case, right? So matrix case, we have whole bunch of eigenvectors, and sometimes the eigenvectors are orthogonal to each other. And here, all those functions are orthogonal to each other in terms of multiplying each other and doing integration. Okay? And so the intuition is that if you want to express your vector in terms of linear combination of some basis, then you can find the coefficient here by taking an inner product of your vector with those basis vectors. And here we will do a similar thing. So what's the inner product of a function is we will multiply them together, then we will take the integration. Okay. And well, there are something extra because those functions are complex conjugate. So when you do the inner product here, you want to do complex conjugation also. It's a complex function. So anyway, let's see how the math work out. So you multiply your function x of t, so whatever function, or I guess we should say signal, so whatever signal x of t, then you multiply with your complex exponential taking complex conjugation. So you take e to the minus j, and instead of k, we use n for whatever reason, because we are going to sum over k here. Okay, so you multiply with e to the minus j n omega naught t. So this n is just arbitrary integer, and then well, you say your x is this summation, so you express this x in the summation ak e to the jk omega naught t. Yeah. So nothing really happened here. You just multiply your function with e to the minus j n omega naught t. And as we say, we do integration over one period. Okay. So you integrate both sides from 0 to big T, where T is the period of your function. Okay. Integration, so this side you just write down integration, this side you write down the integration. And now we do the thing we always do. So we look through everything inside integration and we want to kick out that things that doesn't depend on the variable integrating over. So we are integrating over t, so this stay because they have small t. But this summation doesn't depend on small t and this ak doesn't depend on small t, so we can kick them out. Okay? Because summation is also, well, summation commute with integration. And integration is linear, so we can pull this ak outside of integration. So with summation ak, then this is the integration of e to the j k minus n omega naught t. So this we are just basing using linearity. Okay, then now we are going to see the orthogonal part of our e to the jk omega t and the e to the jn omega t. So this is basically the inner product between our e to the jk omega t and the e to the jn omega t. And so what's this integration? So if k not equal to n, then this is some exponential. Then we know when we integrating exponential, we are just having this 1 over the coefficient here, and we have an exponential here. Okay. And so this is just doing the integration because we have basically e to the at, then it's 1 over a e to the at. Okay. And the upper and lower limit will be big T and 0. And okay, so here we use the fact that t is the period. So t times big T times omega naught will equal to 2 pi. So you have e to the j 2 pi times k minus n is an integer because k is an integer and n is an integer. So you have e to the j 2 pi times an integer, and but e to the 2 pi j is 1, so this is just 1. So upper limit is 1, the lower limit is e to the 0 is obviously also 1. Okay. So this is 1 minus 1, so this is 0. Okay. And this is something finite because k not equal to n. And okay, so for k equal to n, this is not correct because this k minus n is 0, and this upper minus lower is also 0, so you have 0 over 0. But you can just take a step back and look at this expression where k equal to n. And this is just e to the 0, so this, you are integrating over 1. So you're integrating 1 over a period of 0 to big T, so that's big T. Okay. So here you kind of see what the meaning of orthogonal here. So this thing is this inner product quotation between e to the jk omega t and e to the j omega t is 0 when k not equal to n. So when k not equal to n, those functions are orthogonal, and equal to big T when k equal to n. And I guess this is the important part, so let's see more intuition about this integration. And this integration, you can intuitively feel this is 0 when k not equal to n. Because k not equal to n, you are integrating over oscillating complex exponential, right? So as part of, say, the it's not quite a real part, but let's say this is a real part of the complex exponential, so it is oscillating. And if you are integrating over this over a period, then all the oscillating up and down thing will cancel out, and it will be 0. And here we are taking like k minus n equal to 1, but say if k minus n equal to, let's see, okay. So if k minus n equal to 2, then we will have something oscillating faster. But when you integrate this over one period, it should all still give you a 0. Okay, so whatever k minus n is, so if it is larger, this will oscillating faster. But if you're integrating over one period, this will give you a 0. But excuse me, this okay. But if when k equal to n, then this thing is no longer oscillating, it's a constant function, so you're just integrating 1. And if you're integrating 1 over a period, then that's just the length of your period, big T. Okay? So this is the thing we'll see throughout the whole course a lot of times. So I guess any question about the derivation here? The intuition or the math here. So we are seeing that the orthogonal property of those harmonic complex exponential. So once again, if you are taking the inner product between e to the jk omega naught t and e to the jn omega naught t, where inner product means well, there are different definitions, but for now, we say you multiplying together, so you take a complex conjugate of one of them, then you multiply them together, and you take the integration. Then you see that this is a 0 when k not equal to n, and it is some value when it is, and it is some positive value when k equal to n. Okay. And anyway, so mathematically we arrive at this. And back to our problem of how to find in AK. So we take this integral, then we see that this term is 0 except when this is 0 except when k equal to n. So those summation, so it's like a delta function, right? And so this summation, you don't need to sum them because you are multiplying something that's 0 except when k equal to n. So you can just put an here, right? So this thing is, okay, we have it here. So this thing is 0 except when k equal to n. So let's just have k equal to n here. So you have an. And when k equal to n, this is big T. So this is big T an. Okay. And so this is left hand side, we keep it as left hand side. And right hand side is what we want, so we got an out. Okay. So we no longer have a summation because we have this delta function here. So we have a single order an here. Well, it's multiplied with some t, but we can just divide big T from both sides. Then we arrive what we want to get. So an equal to 1 over big T. Integration from 0 to big T x of t e to the minus jn omega naught t dt. Okay. So you multiply your x of t with e to the minus jn omega naught t. So basically complex conjugation of e to the jn omega naught t. Then you integrate it over one period and you do some normalization with 1 over t. Then you will get back your an. Okay. So yeah. So this is the first example of a large family of back and forth Fourier transforms. So this is a Fourier series. We see that we can transform back and forth between x of t and ak. Okay, oh, I should delete this. Okay. So this is not needed, so let's close it out. Okay, yeah. So we have seen ways to express this back and forth. So we want to express x of t in terms of the summation of harmonic complex exponential. So if we have a whole bunch of ak, then we can write x of t as summation k from minus infinity to plus infinity, ak e to the jk omega naught t, or you can write omega naught into 2 pi over t. And so those are called synthesis equation of Fourier series. That's how you synthesize. So the idea is you want to synthesize your function x of t from your harmonic complex exponentials. And the other way around is you have x of t, then you want to calculate those ak, or you have an here. Okay. And okay, so I actually should write k, but doesn't matter. Okay. So if you have your x of t, you want to get ak, then you can do the thing we just derived. So, well, for now it's an. So an is 1 over t, integration t and x over t times e to the minus jn omega naught t dt. Okay. And also you can write omega naught instead of big T here. Okay. So, question about how we get those equations. And so here we basically prove what we say before, right? Because we have a very deterministic formula for an, so that means those ak here are unique, because for every ak you can just calculate them in this form. So the set of ak for a given x of t is unique because you just calculate them in this way, and well, those calculations have a unique answer. And some more detail here. So you see that we are a little different. So here we say 0 to big T, but here we write integration with big T. And it means that we are integrating one period. Okay. So because the derivation here is big 0 to big T doesn't matter. You see this cancellation. It should happen for whatever big T interval. You don't necessarily need to start at 0. Okay. So yeah, so we express that with this form of integration over big T. It means you are starting from whatever small t naught to small t naught to big T. Okay? And but anyway, most of the time, well, depends. And but anyway, a bigger, very good choice of the t naught a lot of time is you pick t naught equals 0, and you back to a thing that we have. So integration from 0 to big T, 0 to big T. Okay. And okay. And a little more names. Okay. So those AKs are called Fourier series coefficients or spatial coefficients, because there are coefficients for those Fourier series. There is a series because you are summing over a discrete number of k's, okay, from -infinity to +infinity. Okay. And also for k equals 0, it has a special name. So this a sub 0 is called the DC or constant component of your signal a sub t. And we can write down it from here. And it's from here, and you see it's a nicer form because k equals 0 here, so this exponential goes away, so you're just integrating x of t over y interval. And you are divided by 1 over t, so you see this a naught is just the average of x, right? The average of x over one period, and it's the average of x. And I guess at high level, although we don't, so something that we'll see more is that, so you can see this as a transformation of x of t, transformation between x of t and this state of ak. So you can see this as a transformation back and forth between x of t and ak, because you see the amount of information in x of t and ak are the same. Because if you know all the ak, then you can calculate x of t from this equation. And if you know x of t, then you can calculate every ak from this equation. So you can either express your function in terms of x of t or express your function in terms of the state of ak. Okay. So they are kind of looking the same signal in different perspectives. And we'll see more examples of this in later part of the course. And this is kind of what we talk about at the introduction slide, where we say we have a function and want to see a different linear combination, etc. But anyway, so this is x of t and ak. And this is, we have 10. Yeah. But you see that now this is a bit funny, because if you count the number of variables here, so ak, how many ak have? You have countably infinite ak. So ak has k from -infinity to +infinity, right? So ak, you have this countably infinite number of scalar values, okay? And but how many variables do you need? Can you get in this x of t? So x of t, if you think about x of t in terms of like integral of impulse functions, so it's like have one value at every t, but t is a computing. So x of t can be like any value at ht, right? And now t is a continuous variable, it's a periodic, so it's t from 0 to big T, but it's a continuous variable. So it seems that there are more information here because the number of coefficients in x of t is more than ak. But so you see there is some mismatch in the number of information here, but we'll see, I guess, next week that that's because we need some regulation on x of t. Not every x of t can be expressed into this summation. Okay? So you need some smoothness in your x of t. But yeah. does sound very high level thinking. Anyway, here is some supplement material about alternative forms of Fourier series. So those will not be in your test, but actually probably very useful in your life because these are different conventions that we will maybe see in different courses. Okay. So this is the form we take in our so different forms of Fourier series. And first is sometimes people instead of writing in terms of omega, so we have those e to the jk omega naught. Instead of omega naught, they will use the frequency. So this how do I say? So this is a different unit of frequency. So this f equals to 1/t. Okay. So you are counting a frequency instead of 1/radian. Instead of a radian per second, you are counting a frequency in terms of like how many rounds per second, how many circles per second. Okay. So sometimes people will write the Fourier series in terms of the frequency. And also sometimes people will write this back forth transformation in terms of in this 1/√t form. Because you see these two equations has some symmetry between them. Because this has 1/t, this don't have 1/t. And so in some place you will see this kind of convention where you want a very symmetric equation, both x over t and the ak has 1/√t here. And so when you guys moral of the story here is when you read different books and read the Fourier series transformation, then you need to be careful about the convention first. So you need to read the convention and make sure how they are normalizing everything. Okay. So that's something useful for your life. Back to our course. Let's see more example of our Fourier series representation. So here we have a very easy example. Okay. So once again, our x over t is in terms of sine and cosine. Now it's in terms of sine. So x over t equal to sine omega naught t. And once again, we can break this into complex exponential just by using reverse Euler. So here we don't really need to do this integration. We can just use our eyeball and break our sine into e to the j omega t and e to the minus j omega naught t. And there will be has a coefficient of 1/2j and minus 1/2j. Okay. And if we break it into this form, then you can just read the AK here, right? Because it's already in this form. So we have A1, which corresponds to this 1 omega naught t, equal to 1/2j, and A minus 1 equal to minus 1/2j. Okay. Okay. And all other AK are 0. Okay. And we can check that this is a real signal. So this AK and A minus k need to be complex conjugation of each other, and that's true. Because your complex conjugation now this is purely imaginary. So you take complex conjugate, this is get you a HR minus psi. Okay. Question about this example. And obviously the big T, the fundamental period here will be 2 pi over big T. Yeah. Okay. And now let's see a more complicated example, but still kind of the same. Okay, so x now is a whole bunch of sine and cosine. So 1 plus sine omega naught t plus 2 cosine omega naught t plus cosine 2 omega naught t plus pi over 4. So a lot of terms, but you can all do your reverse Euler to break them into e to the plus minus j omega naught t. So this sine become 1/2j e to the j theta minus e to the minus j theta. And the cosine become 1/2, then 1/2 cancel with your 2, then e to the jcx, e to the minus jx. And similarly, this cosine e to the jx, e to the minus jx, but now your x has a 1/4 here. Excuse me, your exponent has a extra pi/4 here. Okay, and now remember we want to express x over t into this summation ak e to the jk omega t. So we need to group all the things with the same k together. Okay, so yeah, so we look through things. So here we have e to the j, we have k equal to +1, k equal to +1 here. So those two things you need to group together. And you group them together, you have coefficient 1 plus 1/2j. And you have k equal to -1 here and k equal to -1 here. And together you have this coefficient. And then those things you have extra pi/4. But that's just, but you can break the exponential, and that just give you a extra e to the j pi/4 multiplying on your ak. And here you have k equal to 2 and k equal to -2. And those extra pi/4 give you this extra factor. And yeah, so now this form is already the summation ak e to the jk omega t. So if k equals 0, k equals 1, k equals -1, k equals +2, k equals -2. And the coefficients are here. So we are listing them here. Okay, a whole bunch of things. And yeah, you can once again check the real condition. So a -1 equal to complex conjugate of a +1, and a -2 equal to complex conjugation of a +2. So the real criteria works, and so you have ak from -2 to +2, and all other ak equal to 0. Okay? And here we have some plot of our ak in terms of k. So only non-zero value of ak is from -2 to +2, as we said. And because now ak are complex values, so we plot this ak in 2 plus, so we have the plot in the polar coordinate. So we have the absolute value of ak and the angle of ak. Okay. And here you see kind of the transformation back and forth between x over t and ak now, right? So remember, this ak, those two plots, will contain all information about your x over t. And you see that this is kind of a more efficient representation here, because here you are just recording 5 complex value, and for x over t is something that extend to plus infinity and negative infinity. Okay, so if you plot x over t, then it's something very complicated that will extend throughout all the time. But if you plot the ak, then this also contains all the information about x over t, and it's just 5 complex number here. Okay, that's pretty cool. So we can kind of plot the function in terms of k, because we plot those ak. Okay, now we're a little ahead of ourselves. Anyway, any question about this example? If not, then let's go to the next example where we actually need to do our integration. Okay? So once again, we want to write x over t instead of summation ak e to the jk omega t. And now this example, well, first it's periodic, but now this is a troublesome function, right? This is a thing that Lagrange thinks that Fourier should not be doing. So we have a signal that's periodic, but it has these sharp corners here, and it actually is discontinuous on those -t1 and the t1 part. Okay, so this is called square wave signal, because we have a lot of square here, and we have it being periodic, so it has period big T. So the signal in terms of formula is 1 when your time is between your time is between -t1 to +t1, and it's 0 everywhere, and excuse me, then it's 0 between minus t2 minus big T over 2 to plus big T over 2. Then it's periodic with period big T, so it keeps repeating itself. Okay. So for every big T, it has this length 2t1 block with height 1. Okay. So it's repeating itself. And anyway, so now we use our analysis relation to calculate all the AK associated with this weird XOT. Okay. And A0 is easy. Okay. So as we say, A0 is the average of this XOT. So integrate from, and now, well, as we say, the integration can be anywhere. So you can take an integration from 0 to big T. But quite obviously, the easier integration is you take minus T over 2 to plus T over 2. So integration from here, so you're integrating over one period. And then you integrate over this signal. And here we already do some simplification. But it's 0 except between minus T1 to T1. So you just integrate between minus T1 to T1, and the height is 1. And so the average of this whole thing is 1 over your period times 2t1. Okay. So this is A0. And what about AK? And AK we also put into the formula. So it's 1 over t, and the integration also from minus 1 over and once again integration because your x function only has value from minus t1 to t1, so your limit taking from minus t1 to t1, and height 1, so the function value is 1, then we ignore, and then you need to multiply with your e to the minus jk omega naught t. This is the thing. So once again, remember although we have n here, so but which is AK, so it's e to the minus jk omega naught t. Okay. So we need to multiply our function with this e to the minus jk omega naught t, then integration over. And this integration you can just do when k not equals 0. Then once again, it's the integration of exponential, so you get 1 over a here. So this is 1 over minus jk omega naught t. And then from t1 to minus t1, and then you just plug in, then you have and then you deal with all the negative sign, etc. Then you see you have e to the jx minus e to the minus jx, so that's proportional to sign. And you clean all things, then you see you have sine k omega naught t here, and over k pi, where we simplify this omega naught t because we know omega naught t equals 2 pi. So we can simplify all those things to just 1 over k pi. Okay. So yeah. So we see AK equal to sine k omega naught t. Sine k omega naught t1 over k pi. Okay. So well, check. So this is good, right? So this is a function of k, and it's well defined for every k not equal to 0. When k equals 0, it will be 0 over 0, but we do the calculation here as a special case, and it depends on the constant omega naught, and depends on the t1. And if you don't like omega naught, then you can remember omega naught equal to 2 pi over big T. So this is k and 2 pi big T1 over big T. Okay. Question. And yeah, once again we can plot those AK in turn on this k line. And now you see we don't have finite value of k. So we actually have infinite number of AK, because this is basically non-zero for every k, right? And so it's 1 over k times sine k. So sine k will be oscillating, and but it will decay with this 1 over k. So, but obviously it depends on the relationship between T1 and omega naught. And another way to say this, because omega naught is 1 over 2 pi over T, big T. So it depends on the relationship between T1 and big T. And here we are plotting this with different T1. Okay. So you see that if T1 is smaller, so when you are, so we are getting smaller and smaller T1. So if this square is getting thinner and thinner, this distribution on AK actually getting spread out. This is some general phenomena we will see later. Yeah. But anyway, for now you see we have those distribution of different AK. So it's AK is oscillating and is decaying with this 1 over casing. And A naught is 2T1 over T. Yeah. And 3 minutes. And okay. Yeah. And as we say, AK is real. And I guess we can also check something. So X of T is real. And we can check that AK star equal to A minus K. And it's true because AK star equal to AK since it's real. And A minus K, when you take minus K, so you have this K become minus K, this K become minus K, and then cancel out. Because sine minus K, sine minus X equal to minus sine X. And anyway, you see this AK, we plot that here. And the interesting thing here is, as we said, this is X is continuous, discontinuous. But all those e to the jk omega naught t are continuous. So how does that make sense? You adding together a whole bunch of continuous signal, then you get a discontinuous signal. So I guess easy answer is because you are summing over infinite signals. Okay, so this series you are summing from minus infinity to plus infinity. So we are saying even though all those signals are continuous, when you summing over an infinite number of them, the limit can be something discontinuous. And but there are some tricky point about this. And also, what kind of signal can you actually express in terms of those this Fourier series representation? Excuse me, here. This Fourier series representation. So we see that this is maybe a little more general than we think. So even though those are smooth and continuous function, we see that some discontinuous function can probably still be expressed in this way. But there are also very bad functions that you cannot express in this way. And we'll see those conditions next time. Those are called Dirichlet conditions. Okay. So we'll see what conditions that give you convergence in the summation of series, and we will also give a little more rigorous meaning of what do we mean by convergence of this series. Okay? Because in your usual calculus, convergence we are summing over a series, but a series we are just summing a number, so convergence is just you become a number. But now we are summing over functions, and they are varying values. So we need to be more careful about what we mean by a convergence of summing over a whole bunch of functions. Okay, so just on time. And any question? Otherwise, it will be today. The course will be stopped. Okay. Okay. See you next week.第二章，其实我们也没有出过，对不对？后面就可能有 filter 的人不知道出，对啊 filter 我们在这里教，对啊，其实我们没出过 multi-dimensional， 对不对？没有。对 multi-dimensional 那就没差。我只有两个是对啊，基本上是2次对，其他没有。 期中考会有2次，所以星期一次期中考快要发生了，应该在2个礼拜就发生了。
对，
所以是2个礼拜。
对，预计是2个礼拜后。